Is this visible?
Yeah,
Let me know when the font size is okay. I think this is fine, right?
yeah, fine.
Okay. So today we will begin with introduction to Astropy. So Astropy is a Python library designed for astronomy and astrophysics, and it is used to handle units, coordinates, manipulating FITS files. FITS is a type of image files used in astronomy. So we'll see what those type of files is. So the first thing is everyone please ensure that you have Astropy installed by just running this command. It's pip install Astropy. So once that is done, let us import the library for that we'll need. So the first thing that we'll begin with is Astropy units. So in yesterday's assignments, you saw that we only use numbers and units I had mentioned in questions that we'll use meters per second or everything. But what if we want to use units within our code? Because sometimes it matters units we use and what conversions we make within our code. So Astropy has this nice little module called Astropy units, very handy. We'll import astropy.units as u. So in our whole code further, we'll call this module as just u. Astropy.units as u. So let us just see what all we have here. If I just press u dot and tab key, I get a list of what units I can use. It has astronomy as well as physics units and more. So let's just take simple, just try meter. So in our output cell, I can just see meter. There is nothing, there is no magnitude, like not 1 meter, 2 meter. It's just meter. It's just a unit for now. But once we multiply this unit by some number, we get 2 meters. So even in the output cell, it is printed in LaTeX code. Whatever equations, whatever units we write, it is formatted in a nice equation. And if we perform mathematical calculations on them, suppose I have radius is 2 meters, and if I say diameter is two times of that, I can print D and it will retain that unit. It will be printed as 4 meters. So I can perform mathematical calculations on my variables which are defined with units. Now we can see what kind of unit it is. So for example, if I just do u dot m dot physical type. So this will give me that this unit is of physical type length. Similarly, I can test like if I use seconds, physical type. It will tell me that it is of the physical type time. Now let's just try some different unit. Suppose I say joule. Joule physical type is. It will tell me that this unit can be used for energy, torque, and work. So this physical type tells us if we can convert these units into each other or not, because the units have to be compatible if we have to convert them into each other. Now there is one important command called decompose. So decompose will just decompose the unit into its SI unit or CGS units if we want. So if I just say u dot joule dot decompose, it will give me its corresponding SI unit. So joule is just kg meter square per second square. And this can be converted into CGS that we'll see further how to do that. But this helps us to identify what physical type it is, what units it is, what all units can we change it into, and to see a list of units that we can convert joule into. There is a function. If I type u dot joule dot find equivalent type. So there is a function called find equivalent units. So find equivalent units will give me a list of units and their SI units in which I can convert joule into. So joule can be converted into Rydberg electron volt, ergs, and that. Um, let's just try a few more units. Suppose I say Newton can be converted into dyne. If we have, let's see, decomposed. You can try out different units like this. Okay, so at this point, I think we can do a quick classwork assignment as such. So suppose you have there is a unit called radius of Earth. So you see we have radius of Earth, radius of Jupiter, Saturn. Then we also have mass of Earth, mass of electron, mass of Jupiter, Saturn, Sun, proton, and all of these units. So I want you all to find out the velocity using the formula gm by r. Let me type it here so you can use that. To use this formula, calculate the velocity, take g as, okay, so before that, use this actually. Import Astropy dot constant as const. And here you have constant dot g. So this will give you a value of g, gravitational constant. So use this constant dot g, use the mass of Earth, use the radius, that is radius of Earth, and calculate v. You can use np dot uh, square root for finding the square root, and post your answers in the chat.
The question is use this formula which is shown in the cell number 12 and doing calculation, put your answer in the chat.
Post the numerical answer into the chat, not the formula. So I'll start doing it side by side.
Constant Constant. R should be from constant, right?
Constant, we also have
No, no.
R, I guess. Both units and constant have R.
Acha. But then it will give answer in terms of R units.
No, we can decompose that. So that's what I was going
Ah,
to show in this.
okay.
Yeah. Okay, so let's just see. Uh, np dot s square root we can take uh, constant dot g into r divided by awesome m. So for me, this answer is given in the terms of Earth mass, meters, then again Earth radius in kg, and then second. So this doesn't make much sense, right? But we can decompose this into the SI units. So if I just say V dot decompose, it will decompose it into meters per second. So decompose converts these units into SI units. Do you want me to zoom more? So decompose is a function which decomposes the units into SI units. And further, we can use this to convert like V. We have, this is our V here. If we use V dot 2, we can convert it into its equivalent unit. Like I can say kilometers per second. I want it in kilometers per second. I can also have it in anything. Like this is crazy, but still. So only thing that we have to see is the dimensions are same in all of this. If I give any other thing here which doesn't make sense, like if I give hertz, this doesn't make any sense at all. So this will throw an error, unit conversion error. And it will tell you that these units are not convertible because they're not compatible with each other. Okay. So this to function, the way we use this to function is whatever unit you want to convert, dot to bracket open, and in that we put the equivalent units that we want. Okay, and one more thing that I can show you is we have S day here. S day is sidereal day. So as the this concept was introduced in the morning session, so we also have sidereal day in this, and we can compose this sidereal day to say we can convert this to minutes and so on. Uh,
Interestingly,
some
you can calculate this velocity in terms of uh, the Earth radius per sidereal day, which means how many times it will revolve around the Earth in a day.
Earth radius times sidereal day.
Yeah, that's right.
Does that mean what does this mean?
It will revolve 106 times or 107 times in a day. That close Earth satellite.
Okay, yeah, that's cool. So what all things we saw here is we saw how to get units, constants, how to decompose them into SI units, and how to convert them into equivalent units. Now, what we can do is we can also create composite units, like just like we. So this is the composite unit. We can have numeric operators like into, divide, and power by using these units. So for example, if I have something called 6 into kg into meter per second square, this is just kg meter per second square. So we can have such composite units like here. Someone has raised hand. Is there any question?
Yes, I had an error while importing Astropy. Can you revert back to?
While importing,
There was an error while I was doing this. It shows an error
what is the
while
error?
importing. I wanted to know what is the syntax for to import Astropy units.
So
Now it is
astropy dot units has yeah.
okay. Thank you.
And then we have astropy dot constants as whatever. I use const. So you can use just C or anything else.
Hello, I have a question. Uh,
Yeah, yeah,
can you go back to that velocity solution where it is 7.9 kilometers?
yeah.
Yeah. So it is 8.169, and then after changing that, we are decomposing unit. Why are the numerical value changing? I mean,
Because here it is the mass of Earth and radius of Earth, right? So that also has numerical value.
okay,
So it
okay,
will adjust it accordingly.
okay, okay.
That's why Astropy is so powerful and it is used in astronomy because these type of conversions become easier. It also takes care of what the value of the variable is.
Yeah. Got it. Thank you.
Yeah. So let's go further. Mm, Okay, so just wanted to show an example of how we can use this in real life. So luminosity represents this total power emitted by the source in all directions. And we derive it from the flux density, distance, and the bandwidth of the source, bandwidth from what we are detecting it from. So the flux density, the unit is used Jansky, which is just 10 to the power 26, minus 26 watt per meter square per hertz. And we use this formula to calculate luminosity and flux density's relation. So 4 pi r square is the surface area of the sphere. This term scales the density from the observer's measurement to total power because we are looking only from one direction, but we want the power emitted in a sphere around the star. S is the flux density, which is the power we receive per unit area per unit frequency at our location. And this delta nu is just the bandwidth over which we measure the flux density. So we can just define it. So 4 pi, then we have r squared. Let's say it is 0.1 gigaparsec away. Gigaparsec. I have to square this multiplied by suppose it's 5 Janskis, and the bandwidth we are observing is 500 megahertz. So this will give me units in gigaparsec square, Jansky megahertz. But this doesn't make much sense, right? I would want it in SI units. Let's decompose it. We get this. And further, these are the unit of watts we can check. So these units are same, meter square kg per second cube. So we get the answer in units of watts. What if I want it in CGS? So I can just convert it luminosity dot 2 or per second. So I get this in CGS units, and it also adjusts the power of 10, if you see. So in SI units, it's just 10 to the power 33. In SI units, I get 10 to the power 40. And this is because if we use org.decompose, we can see the only scaling factor is 10 to the power minus 7. So that seems correct. Now, the next thing that we can do is, if I have a list of distances, suppose I have any random value, 6, 7.8, 9, I can multiply this list by any unit or any composite unit. And if I print this distances list, so this unit is applied to the entire list. So all of the elements in this list will have this Astropy unit. And if I take any one instance from the list, suppose distance is 1, that is the second, this unit is retained with that. So I can use this list in my calculations, and all the calculations, even in for loops, this unit will be retained with it. Someone has raised hand. Is there any question?
Sir, can you show me the first value for the luminosity with the gigaparsec unit?
Yeah.
Sir, if you use Jansky, is it compulsory to use gigaparsec or can you use any other unit also, sir?
You can use any other unit. So it's just distance, Jansky, and frequency, right?
So if you use
This is
it
just an
instead of
example that I
Jansky,
took.
can you use light years, sir? Instead of
I'm not
gigaparsec,
sure.
use light year.
Maybe you can. Right here. Okay, I have to type the whole thing. Yeah, that will work.
Okay, sir.
Values will be different though.
Okay,
So
sir.
this changed to 2.8 instead of 2.9. Yeah. So
One
yeah.
of the one of the points that I want to emphasize here is astronomers generally may not prefer unit of light year because there is generally no way of measuring the distances. So one of the useful method is parallax, and that gives you directly parsec. So astronomers prefer to use parsec as a distance rather than light year.
Okay, sir.
Someone has asked what the extension name is U and V. I don't understand which. Are you talking about this U? So this is just I've imported the astropy.units module as U. So u.org is just calling this unit from the astropy.units module. Show the cell which defines distances. This one. Okay, so we can move ahead a bit. So when we have to decompose something, suppose I decompose Jansky. I can always use dot two and then convert it into CGS units. But in decompose itself, we can pass an argument called u.cgs basis. So this will convert it into CGS units. So we can check what all these CGS and bases are. So if I just check CGS basis, so these are the units Astropy uses for CGS. And similarly, we have SI. So they are mostly similar. The only difference is CGS does not have ampere, and I think rest all is same. Only kg is converted into grams, meter in centimeter, And I think that's the only difference. Okay. So there are some limitations for using these quantities with the NumPy arrays or something. I have given a link for that. You can check that for yourself if you ever face any issues using it with NumPy. So I can just give an example how we can use it with NumPy. So like you remember from yesterday, sine 30, 30 is considered as radian. And for that, we usually use this, right? We convert degree to radian and then pass 30. But in Astropy, we can also use this sine 30 into u dot degree. You see the formatting is different. Here it's like the text is different, but here it's different. So this is, again, the output is in LaTeX and this is dimensionless. So this converts it into that format. And if I do something like this that we have already seen above, but still, this will give me kg square and applying square root, np dot square root on this. Okay, so it has to have some value. So square root will actually also act on the units, just like
Is
it would
that double
happen.
one required? Double one may not be required. No?
Correct. Okay, so astropy.constants, just one, we already saw this above, but just you can see the list of uh, constants that are available for us. And if you want information of any of those constants, suppose they are Jupiter, I can use print function, and this print function will print all the data that is there about this. So it is the nominal Jupiter equatorial radius value, what is the uncertainty units it is measured in, and where we are pulling this data from. So it is some resolution B3. So mostly it is this one data or some other databases that it pulls this data from. Okay, so let's move ahead with equivalencies. So sometimes there are equivalencies that we use while we do manual calculations. Like we know that we can convert mass into energy. But if we try that using Astropy units, if I try converting kg dot to EV, it will throw an error that this is a unit conversion error. We cannot convert mass into energy. They are not convertible, but we know as a fact that we can actually do it. So we use something called as equivalencies in it. So as this link has a table of equivalencies that we can use. I'll just show you quickly a few of them. So let's consider, for example, we have mass of electron. Now I can convert this mass of electron to mega electron volts. This will throw an error because it will again say mass and energy not compatible units. But if I give one more argument here, equivalencies equals to U dot mass energy equivalence. So this mass energy equivalence has inbuilt functions which allows these kinds of conversions. So this is converted into mega electron volts. Now similarly, like mass energy, we have other equivalencies like parallax equivalencies. Suppose we have distance in arc second, we want to convert it into parsec. It will say it is not compatible units, but we know for a fact that it is. So suppose you have arc seconds, 2, yes, parsec, and in equivalencies, we'll use u dot parallax. It will be converted into parsec. Just like this, there are these kind of equivalencies like Doppler redshift. It is used to calculate some dimensionless redshift value to speed. So suppose we have z of 0.4 and I have to convert it to kilometers per second. Then I'll use z dot 2 kilometer per second, and I need to type always this equivalence is equals to, because the third argument is always equivalencies in second argument is always equivalencies in two function. So I can just say u dot Doppler redshift. All these are the other equivalencies: Doppler optical, radio, redshift, relativistic. Now this is going to throw me an error. This will say that the float object has no attribute 2. This will happen when you are using Astropy functions on some number. Astropy doesn't know what the unit of this is. Even if it's unitless or dimensionless scalar, it still needs to know that it is that. So for that, we need to multiply this by u dot dimensionless scaled, unscaled. So this function just gives it no unit. No unit is also necessary to perform Astropy functions on it. Now this will be used to convert it into kilometer per second. And one last example is wavelength to frequency conversion. Suppose we have wavelength of 500 micrometers or nanometers. We want to convert it into frequency. So we just add wavelength to hertz. So this will give an error again. And it will tell you that length and frequency, these types are not convertible. But if we use equivalencies, there is this equivalency called spectral. This allows us to convert from meters to hertz. So this is just 4 examples that I showed: mass, energy, parallax, Doppler redshift, and spectral. But there is a whole list of other equivalencies that you can check on the documentation page. And they have also given examples for each of those equivalencies. And suppose if you are working on some research topic and there is no equivalency that you want, you can also have your custom equivalencies. So writing new equivalencies, there is a method how to write your own equivalent units. And they have given a tutorial for that here, quantity object. So you can check that out later. Now let's move ahead with, oh yeah, before that. So one more thing that I would show. If I use hertz, find equivalent units. It is giving me that hertz can be converted into this these units. But if I use hertz dot find equivalent units, and in bracket I write equivalencies equals to spectral. While finding equivalent units, if I pass that I want in spectral equivalencies, then it will give me whole other bunch of units that I can convert hertz into using the spectral equivalent unit.
Can I ask a question?
Yeah.
Sir, is there any way that we can express our normal units into natural units always?
In the sense?
In the natural unit, we express C equal to Kb equal to h cross equal to 1. In cosmology, we generally use it. So in Python, is there any way that
Yeah, you can just define it as a variable, whatever you want.
No, he's talking about Planck units, so you can directly Planck units can you use? That is the question, I think.
I'm not sure. Maybe Jigar can check and answer in chat if it's possible. I've never seen that. Okay. So let's go to coordinates now. So let's import another module from astropy.coordinate. Import sky coord. So this is spelled with double O, this function name, this module name, okay? Sky coord. So let's say we have,
Somebody wants to see the last syntax.
sorry,
Somebody wants to see the last syntax. I
the
think it's for
spectrum.
equivalency. I think you can move ahead now.
Yes, I was just looking at the comments. Okay. Okay, so suppose we have the right ascension and declination of Pleiades cluster. Then I can use that to create coordinates using right ascension as 56.85. I've checked this from Wikipedia, and declination of 24.1167. Now, what this frame ICRS is, I have put information about it in the notebook that I'll share with you later. So usually use frame ICRS, or there is other frames like FK5 and other frames, but mostly we use ICRS. And we need to mention that these units are in degrees. So this is 56 degree, 56.85 degree and 24.
Yeah, I have a question.
Yeah.
If you go to the instruction, from astropy.coordinates import skycord when you're mentioning. So what does it indicate? I mean, astropy.coordinates is a library and skycord is a table or something like that, or what
No,
is
no.
it?
So whenever I import anything like this, so astropy.coordinates is a module which has many functions. From that, I'm importing skycord. So as
So,
yeah,
so then in that case, suppose I put astropy.coordinate.skycord and import that, will that
as
work?
yeah, that will work. From
No, not from
astropy.coordinates.
astropy. No, just import astropy.coordinates.skycord.
Like this.
Huh.
Okay, so skycord is a function in this module. It is not a module in itself. That's why it won't work.
Okay.
So someone in comments is asking what is ICRS. So ICRS is the frame of reference that we use. I have put that information about it in the notes that I will send. I won't explain it here. Yeah, you can import astropy.coordinates, but then you'll have to write every time astropy.coordinates.skycord. RA and dec are right ascension and declination. It was covered in the session before this. Okay, so let's just try to print playlists. So this gives us this coordinate units here. Now, SkyCoord accepts the coordinates in HMS, DMS, that is hours, minutes, seconds, and degrees, minutes, seconds format, or in degrees format. So if we have in HMS like this 3 hours, 47 minutes, 24 seconds, and if we have declination in this format, plus 240700 seconds. We can use this to create a chord. So this will also work. Now notice the difference that if I pass HMS DMS values, the print will still print it in degrees in the both. So Astropy converts that automatically in it. And we can see that by using this. If I want playlist.ra.degrees, so this playlist is defined as 5 coordinates using HMS DMS format, but if I want it in degrees, I can just call this function and it will give me in degrees value. Similarly, we can do for declination. So this is useful in converting to different coordinate systems.
So if IC
Now,
arrays is not mentioned, that also should work, right? So, it may take default.
I think ICRS is default only.
Huh.
Yeah. Now, suppose we don't know the Aryan declination of some object. Suppose, say, Aldebaran. SkyCoord has this function called from name. So from name, actually, we can put name of star in it. And it will give us the coordinates of it. Now, how does this work is this from name function fetches 3 different catalogs like Simbad, NED, and VZR catalog. And from that catalog, it fetches its coordinates. And I think even if I type small a, it will work because it uses regular expressions in the background. So it looks for closest match of the name. So small spelling mistake might be possible, but I have never tried that. Just guessing here because they use regular expression. Maybe it uses the closest match approach. So if we have coordinates of 2 astronomical objects, we can find separation between them. So say separation equals to Pleiades dot separation Aldebaran. So this is the syntax that we use to find separation. So this will find separation between the Pleiades cluster and Aldebaran star and give us the value in degrees. So there is 13 degrees 40 minutes this separation between Pleiades and Aldebaran. This is the angular separation between them. One other quick way is we can just write SkyCoord dot from name is pica dot separation SkyCoord from name after this. So I just put everything in one line instead of defining variables and then conic code. This will take coordinates of spica. This will take coordinates of actors and find separation between them. So from name basically is a function which fetches coordinates of whatever star name or object name you put from catalogs. So it uses NED catalog, Simbad catalog, or Vizier catalog to find the coordinates of astronomical objects. What is separation 3D? We will look into it. So let's just look separation 3D next. So Mizar and Alcor are famous double stars. We have, let's see, from name, Mizar and Alcor. I don't know if forename also passes this. Okay, so from name does not have, so we cannot use this. Okay, so we have these coordinates of these two objects. As you can see, the difference is very small. They're very close to each other. I'm going to define those coordinates again, but in a different way. I will say my right ascension is 200.98. My declination is 54.92. And I'll pass one more parameter, distance is 24.0 parsecs. I'll write similar for alcohol. It was 201.30 and declination is 54.98 and its distance is 24.9 parsecs. If we are giving area and deck in degrees, we need to write that the unit is degrees. Okay. So I think for distances, we cannot use this. Did not know that. Okay, I have written them somewhere else. I'll just copy paste that. So it needs to be in HMS DMS format if we want to use 3D separation. So now we have coordinates, and to find 3D separation, we can just use myjar dot separation 3D alpha. So this separation 3D will give me the distance. And just separation will give me angular separation. So this is the angular separation between them. So they're very close to each other, but they're also very far from each other. So they look like binaries or very close. You wrote aldebrand instead of aldebrand. Okay, I'm just seeing the comments here. What catalogs are present in Sky Code from name? As far as I remember, it's Simbad, Vizier, and Ned catalog. Okay, Jigar is answering most of them, so I'll just continue ahead. Now, one thing that we can do is we can convert coordinates to galactic coordinates by just using dot galactic. So this neither will give us coordinates in galactic frame of reference. So it removes this RA declination distance to LBN distance. So it's the galactic latitude, longitude, and the distance. What else? I'm skipping some examples so that, sir, how much time do we have left? I think it's still 1:15, so
Yeah,
half an hour,
1:15.
right?
So, half an hour.
Yeah, okay. So I'll move ahead. The more examples that I was going to show you, I'll just share the notebook with you so you can follow those examples. Now let's see how we can use Astropy to plan our observations. Let me import some libraries, some functions first. So altitude azimuth is also a coordinate system, ITAS. Astropy is also a time module. And okay, so there is Earth location too. So Astropy coordinates has this module called Earth location. And Earth location has two functions inside it, off address and off site. So we can get the location coordinates of any address of any site. And these sites have some list of observatories in it. So we have an observatory, Indian Astronomical Observatory at Hanle, Ladakh. So this will give me its location coordinates. And I think also its altitude. And suppose we have observation time. We know that we're going to observe, we're planning an observation on some date. So the format is you use year, month, day, and what time you want to start your observation at. So this gives that this observation time is an object in ISO format and its value is this. Now this time actually converts whatever timestamp we put into epoch time. Epoch time is something that is used in computers. So epoch time since 1st of Jan 1970, we have been counting the number of seconds. So that epoch time is used for background calculations. Uh, Now we can find the altitude and azimuth using Alta's function. We'll use location, Hamlet, and observation time is observation time. So this will give us this information about it. That we are using this observation time from this location. What is the pressure, temperature, if we have this information and everything. Okay, I'm just looking for comments here. Can we access Gaia through Astropy? Yes, we can, but we are not going to cover that today. Miser and Alcor are stars. Um, okay, so we have Pleiades coordinates, right? Okay, we have coordinates for Pleiades. So we can transform this
I
to,
have a question here.
yeah,
Sorry, this Alta's function is in which module?
it's in coordinates only. So coordinates has this bichord, altaz, or location, all these
Okay.
functions. Yeah. So now we have this altaz about the location we are looking from and the time, and we can convert Pleiades to this altaz coordinates. And then we can use this to plot a graph and see if we are able to observe this or not. So let's say I'm giving a time range here. So full night, we have observation time plus whatever the delta hours is. So observation time plus 6 hours. Full night altaz coordinates, I'll use altaz. Location as Hanle. Observation time as full night times. And full night altaz words as radius transform to altaz full night.
I think this
So
module
what?
you can go a bit slower.
Yeah. So what this does essentially, I was going to explain that now. I have this observation time. I'm giving it a window. So full night time is my observation time, that is 1 a.m. plus 6 hours. So from 1 a.m. to 7 a.m. So these are my timestamps for the full night. I'm using these timestamps to create altitude azimuth range. So I pass this as full night altaz. I pass it from the altaz function. I'm using the observation time as the full time range of 1 a.m. to 7 a.m. and I'm getting altaz coordinates. Now I'm using this altaz coordinates to get altaz coordinates of Pleiades. And I'm just matching if from Hanle will I be able to see Pleiades between 1 to 7 or not. So let's just see how we can see it. So plot delta hours, full night delta squads. So this is giving me a plot of air mass versus hour. So this is from 0 to 6, starts from here. So it is telling me that I will be able to see Pleiades if the plot occurs. If I change the time here, if I change, say, I don't know, this month, then it is showing me this. So I don't think we can see Pleiades. It's go air mass is going in minus. That's why I'm taking June.
Explain the concept of air mass.
Yeah, so concept of air mass, even I am not that clear to be honest. So I think air mass is just the thickness of air column above that location. More the air mass, the less bright the star will be, I think.
No, I mean, I just wanted you to explain this part only. That
Yeah,
if you look at a globe, for example, if the object is at zenith, then the light is passing through the air with minimum distance. But if the object is near horizon, then effectively it has to pass through large amount of air. And that's why when the zenith angle changes, that is angle from the zenith changes, the air mass effectively goes on increasing, and because of that the extinction starts increasing, so the intensity goes on reducing. So
yeah.
that's why you can't see, for example, the sun at noon, but you can see sun at sunset, because a lot of reduction has happened in the uh, total intensity.
So we are taking this XZ here. This is the second of the zenith angle. So this is used commonly to estimate the air mass. This ITAS function has information like atmospheric pressure also, if it's available. I think for Hanle it's not available because I see it's shows 0. But for some sites, even that data is available, even the temperature, relative humidity, and so on. Okay, so I'll move ahead with the FITs now. This is the last topic we'll see in Astropy today. So FITS files is a type of it is a standard format for storing and exchanging astronomical data. It was developed by NASA and it not only contains image data but it also has a lot of metadata to support it. So it has spectrum data, it has tables of information about whatever stars are there in the image, all of those coordinates of the stars and everything. So it has something called as header data units, HDUs, that store image data and the corresponding metadata. That metadata can also have when the image was taken, what instrument did it use, what were the parameters of the institute of the instrument when the image was taken, and much more data. I'll show you what the data contains. So the header is ASCII metadata in key value pairs. So the headers is basically a big dictionary. And the main data which contains the image data is binary data, often an image or a table. Not all FITS files are image data. Some of them are just table data. So uh, if you try to plot image of a FITS file, but it does not contain any image data, it will give an error because probably the FITS file that you have downloaded has only table data. Uh, so the primary data section is just 2D arrays of uh, images. So it's just channels or whatever channels the image has. So astropy.io fits module will be used to access fits data in Python. And the simple syntax is just fits.open and your file name. So right now I have not shared the fits images with you that you can try for yourself, but we'll be using some example fits that uh, I will share with you later when I share the notebook. For now, maybe you can just observe. Yeah, someone is raised hand. Go ahead.
Yes, sir. So there is an app called QFits View. We can find each and everything there. So while we are using these libraries here to find the fits data,
So when you want to do perform any calculations on them, does the Cupids view have? Because I have not used that software ever.
I think they have because I have used they show graphs and all.
Okay, so when this library will be useful is the graphic software that you are mentioning, you will use it manually, right? You will have one fits file and you will do something manually using click and drag options. But what
Yeah.
if you are getting hundreds of thousands of fits files every day?
Mm-hmm.
Then you cannot open each one manually, do the analysis on it, whatever you want, or whatever research you want to do on it. It's impossible to do every day hundreds of thousands. And
Okay.
there are some large scale sky surveys like LSST or SDSS. They actually download hundreds of thousands of images. They click every day new pictures. Now you want to
Okay.
automate your pipeline for that.
Yes.
So here I'm showing an example just for one fits file, but if you have so much of data, you can automate the pipeline by just reading fits file in the background in the server. No one is going to see those images ever, unless your program finds that this image is interesting, then only you will see it. So for that, we will use astropy.io fits.
Okay. Okay. Thank you.
Yeah. So let's see. Fits file 0. So if I just check what the data is, it will just show me numpy, two-dimensional numpy array. How I know it's two-dimensional? I see two brackets, so it's two-dimensional. So this is a numpy array, and if this is shown, then I know I can plot image out of it. So how to do that? I can just say plt.imshow. I cannot use plt.plot now. I will have to use image show because this is a two-dimensional image. And I will name this one as the image. So I can pass plt.imshow image. Now it is taking a bit longer because the file that I'm using as an example is a 400 MB file. So it is a globular cluster. Now it is not really looking good because we see in log scale and all these are just pixel values. So what I will have to do here is from matplotlib, habit. From matplotlib.colors, I will import something called as log norm. And here I will use that norm equals to log norm. And color bar will give me the pixel value, whatever is in the image. Yeah, whoever has raised hand, go ahead.
Sir, I'm new to the concept of FITS file. Can you
Hmm.
explain what it is?
FITS is a type of, just like we have PNG, JPG files, image files. In astronomy, you use something called a FITS file. So you see the ending is dot .fits, not dot .png or dot .jpg. So those PNG and JPG files are highly processed and compressed files, but FITS is it contains more than image data. Like I mentioned, it contains data about what telescope was used to capture it, what were the physical parameters of that telescope, then what are the each you see each of those dots, that's a star. This FITS file also contains data about coordinates of all of these stars. It might contain spectra of all of these stars. So that's why the file size is like 400 MBs. There is a lot of data in it. So this is a very data-rich file format that is used in astronomy. I'm using color map here so that it's easier to see. Grays will just
Excuse me,
convert it
sir.
into black and white. Yep.
Sir, can we use OpenCV matlab, for plotting images like you use
Yeah,
matplotlib?
you can use OpenCV, but what's the point of it, right? You want to do analysis on it. Plotting, I'm just using to show how the FITS file look. Mostly FITS file are used for some analysis on it. The visualization is just one small aspect of it that we just want to see how it looks or what's in it. OpenCV will not make use of data if so see all of these dots are stars and each of them have a spectrum. That data will be in FITS files. OpenCV will not be able to read that, but Astropy FITS module will be able to read that data.
So what that syntax means, image equal to fits underscore fits 0. What that means, sir?
Yeah. So you see index 0 refers to the primary header unit. So this data contains metadata for the header unit, which is okay. It would be better if I just show you the header first. So see all this data, it is actually not showing everything, but this kind of data is in header. So it has information regarding, I don't even know what all this is, but it has some coordinates. It is taken from Hubble Space Telescope. It is using 814 wavelength, so whatever unit they use. Filter, what instrument, camera instrument they are using, what is the right ascension declination of the cluster. Total exposure, it is using 200 seconds exposure. When was the date of observation? This was clicked in 2016. Exactly what time? Citation, which data release was this published in? So I took this picture from this data source. So this is like I think uh, Hubble ultraviolet globular survey or something. HUGS. I will also show you later how to download bit files and from where to get all the data for this. So this
So how to
zero,
extract the file we need, so how to extract the appropriate photo that we need in the fits files? How do we know that, sir?
that's what I'm saying. I'll show it to you later how. So this is just an example image that I downloaded.
Okay, sir.
Let me see if I can prioritize that first. What all things I have to cover ahead? Okay, I can show you that. So let's see, for example, we use SDSS survey. Okay, so this is the Sloan Digital Sky Survey data access page. Now there is two ways we can get. We can go to the Science Archive server. This is also used to programmatically fetch images, or we can go to Sky Server. Now Sky Server also has multiple options to get data. We can either perform an SQL search. So SQL search will just use select top 100. We will give whatever information we want. So there are many example queries. Suppose we want clean photometric galaxies. This is the query we'll have to run. And if we submit it, it will give you a table CSV. If it has images, only then it will return you FITS files also. But this is a bit complicated way of getting data. The most simplest way for our practice, what we can do is we can go to navigate, which is a visual way of finding. So this is the entire sky survey. Many objects you can see here, you can zoom in. If we click on any object that you might find of interest and click on it, you see here it is giving SDSS ID, what is the RA declination, what is the type, galaxy, and there is this explore option. If we click on explore option, it gives us further data of magnitudes of each of the UGRIZ filter. It is like the UBV filter which was mentioned in the first session today. So these are I think ultraviolet, green, red, blue, and C is in infrared maybe. All these filters and their magnitudes and the errors in them. And there is much more data like cross identification, which other catalogs this object is present in. And then here is the option called fits. If we click on this fits option, we get the corrected frames. We mostly go for corrected frames because it's mentioned here. That's why the final step of processing for each field should be the corrected files to use for most purposes. So if you click on each of those files, UGRIZ, you can download fits files for each of those filters. That's how you get data from one of the sources, that is SDSS. Now there are other sources like even Chandra has their own data, Hubble Space Telescope has their own FITS file hosting platform. From all of those places, whatever object you're interested in, so if the object of interest you already know its RA and declination, you see image options, there is a field RA and declination. Just put that RA and declination, find that object, update the page, and it will go to that object. And then you can see if SDSS survey has picked that object or not. If SDSS has not picked the object, then this explore option is not available. I've rarely seen. Yesterday, while I was just preparing this, I saw one object was not available for explore. Yeah, so most of the things are there, and it's a huge survey, so you can just I don't know it's what is the size of the survey, but yeah. Someone had raised hand. Is there any more question about this? Can you show one more time after navigate? Okay. So there are also other these options, radial search also you can perform. So after navigate, select any object of interest, and then there is explore option here. She's the see this object's complete data in Object Explorer. In Explore object, we can get sometimes you get this warning that this object's photometry data may be unreliable. So they found that the errors are more, or there is maybe something wrong in it. So if you don't want such object, you can just skip it. Can you provide links for getting such data? Yeah, I have provided links. I will, okay, it's not mentioned here, but the notebook I will share, it will have all of the links that I used. There are more than 3 or 4 data sources, Space Telescope Institute that also host some FITS files. But for the people, if you want to just check right now. You can just skip ahead. I don't know why I kept that at last. Um, I'm pasting this code in chat box. Can someone try to run this part of code and see if I think it should run? Yeah, okay, so it's running. What object was this exactly? Does not have header object. Okay, so it's there. So this Astropy utils data get package data file name. So Astropy has provided some example fits files within its code base itself. So I'm using this reprojected SDSS, some green filter. I don't know which frame it is, but it is some fits file which is just as an example file. Astropy has put it in their code. So we can use this code to quickly get a FITS file. It's not as high resolution. It does not even have any headers or any information about the stars or anything. It is just the image. Uh, yeah, you can use Grace color map and log normal. I will show what I was going to do with it later. So for now, we'll just get back to one of the examples. Okay, I'll quickly show this. How much time do you have left? I think it's just 5 minutes, right? Okay.
We have 5 minutes. What we can do is complete this, then we'll have a quick
Yeah.
poll, and the poll will be on small feedback. Yeah.
Yeah. So I'll here just show one of the this UGRIZ that I showed, the navigate thing. I have downloaded the 5 of them. I'll just show one of them how it looks.
Sir, may I ask a small doubt?
Yeah, sure, go ahead.
Sir, if you're if you're detecting some abnormalities and inside the fix file, we want to check a particular point or zoom in and check. Is there a way to search that? Like do a small part of the fix file, like that can be checked.
Basically, you want to zoom in, right?
Yes, sir.
I'll show this in this example. So this is one of the eye filter file. Now, suppose if you want to zoom in, this is some galaxy structure that I can see here. If you want to zoom in on this one, either you can use copy this image in new tab and zoom it like that. But if you want to do it in code itself, then you can put x limit, y limits, or you plot it using matplotlib widget. There is a zoom feature in that. But I'll just show you how to do that. So if I say x limit, to save time, I'll just copy the code that I've already written. X minimum, x maximum. Now suppose I want to get to this galaxy. So it's like from 0 to 500. Y minimum. Y maximum, we have, where is this line? 1000 to say 1200, maybe 800 to 1200. And I can use this here from X min to X max, Y min to Y max. Now this will just zoom into a specific region of the code. Okay, I missed the galaxy totally. What's that? Because it's okay, it's starting 0 from above. I need to invert the scale. Okay, you get it. This is matplotlib manipulation, so you can invert the scale. So this is how you zoom. You put X and Y limits, and you just pass it as a indexing here. So start from X minimum, end to X maximum, start from Y minimum, start to Y maximum.
Hello, sir.
Yeah.
Sometimes we are writing in syntax from module name, then import, and sometimes just like numpy, import numpy as. What is the difference and when we will write from module name import and when
Okay.
import as?
Okay. So import matplotlib.pyplot as plt. We use this, right? Okay, I can show one more example that we already used. I can write it two ways. Import astropy dot units as u. This works. So this is basically we are importing astropy dot units module as u. But I can also write it as from astropy import units as u. Both are the same thing. This is a shorter way of writing it. Astropy dot units, astropy dot whatever functions I can write. But I can also write that from astropy, I want to import units module and rename it as u. Both are the same things. So it just depends on your preference. I'm using import numpy as np because I have to import the whole numpy library. I don't want anything from specifically from numpy. But I can do it if I want to. If my code only uses one module from numpy, I can import just that one. Hope that's clear. Okay, so the next thing I'll quickly show is just one last thing, false color images. So sometimes it also might happen that
Okay, sir. So that means whenever you write.
hello. Hello.
Hello, sir.
Yeah.
That means whenever you have written from astropy dot coordinates, and it can be written like import astropy then from coordinates like that.
No, you cannot write from after.
Okay.
Yeah.
Sorry.
So
From astropy, import units as u, and import astropy dots unit as u same. That means
yeah, both of
it
them are same.
depends on the it depends on it depends upon me.
Yeah, it depends on you.
Okay.
So it is the feature of Python language. How do you import libraries and then sub libraries inside a bigger library?
Correct. So the terminologies used are libraries, modules, functions. So astropy dot units, units is a module, unit has its own function.
Okay, sir. Thank
Yeah.
you.
Okay, so just quickly move ahead. So I specifically wanted to show
Can I
this
ask a
one.
quick question, sir?
Yeah, sure.
So what does the CMAP equal to gray means in that coding?
CMAP just means color map.
So I can put any color that available in that
Any color map that you can use. I'll just show this now. So I'm using grays because it's converted everything black and white, easier to see on the eyes. So color map scales pixel values. So if we have 0 to 255 pixel values, it scales according to whatever the color map we use. There is something called as Viridis, Inferno, Magma. I think there are hundreds of color maps in Matplotlib. Whatever looks better, we use that.
Then also that what that the bar represents on the side of this graph, sir, it's 10 power 1, 10 power 2. What that is means, sir?
I think it's pixel density. So whenever the signal is collected in the CCD sensors, how much photons did it collect? I think it's the count of that.
So it
I
means
will
at
have
the
to
signal
check.
of 2000, there are 10 power 4 photons collected like that, sir.
Yeah, because this is a 200-second exposure, so it's a very high exposure image.
Okay, sir. Okay, thank you,
This
sir.
is a log scale, yeah.
Yes, sir. Thank you, sir.
So sometimes when you open some PIT file, it looks like there is nothing in it. But you see, there is some black dot here, some black dot here. At first, I thought these are specks on my screen, but even when I scroll, they're still there. So there is data in it, but it just feels like there is not much data in it. So sometimes you need to extract data. I have less time, so to save time, I will just copy code from the notebook that I'm going to share with you. I'm not going to write everything here now, and I will explain the code. So just instead of plotting, what I here did is I converted whatever nan values are there to image to some number that is 0. And then I took the minimum and a maximum. I set cutoff. So whatever the 50 percentile image, whatever the 50 percentile of lower values in this images, I ignored them. And even the maximum 99.99 above that, I ignored the cutoff. So most of the faint stars in it will be faint data in it will be removed, and only the top 50% between 50 and 99% percentile will be considered. So if I do that, I get some enhancement in the image. So see, there are these many stars there, but they were not visible because probably of the background noise or maybe the exposure of the image. But there is a lot of data in it and a lot of stars in it. If I play more with the uh, thresholds, the cutoff lower and upper thresholds, and apply it in the log norm, I will get more data out of it probably. So this is the pixel intensity in log scale. So I limited that pixel intensity to this 10 raised to, you see 10 raised to 4. It starts and ends 10 raised to 4. But in the above image, you can see if I don't give any, it starts from 10 to the power minus 2. So it depends on what the exposure of the image is, what uh, pixel densities are you looking for, and so on. And I think I should stop here, but the notebook, I will share it with you. It also has some false color images, like how the false color images are created. You can see those examples. Or maybe I should show them to you. Wait,
Yeah, I
because
will, Pratik, we can,
yeah,
because we have to take a break.
yeah.
But yeah, you complete this part without starting a new thing, and we can see whether we can have something extra time later.
Yeah. So this is one of the Cat's Eye Nebula and Hubble Space Telescope image. So this is the green band, red band, and blue band. So these are the 3-band filters. And you can notice there is some difference in the images here because these are different color bands, different frequencies. Now the pretty images that we see, they are used basically by combining these 3-band images and color grading them. Like we assign colors, that whatever is the G band images, we'll assign it green, red, and blue, and so on. And we can do that in Python by doing something like this. So first thing that I did here was to normalize the data, take the minimum maximum of pixel values and scale them accordingly, minimum and maximum scale. After normalization, I split the channels into three RGB channels. And this R normalized, green normalized, I normalized, I assigned them to this RGB image, three channels. And then I plotted that image. So that will create all the good looking images that we see in PR, public relations, the press release and all those images. So these are not real. Like if we are near this nebula, I don't think we'll see it like this. But yeah, this is how color grading is done. Yeah, so I'll stop here. I'll share the
Uh,
whole
I
notebook
will
with you so that you
share
can
the
play with it.
poll.
Sir,
I'll
can you
share
please
the
explain the last set of two codes?
poll.
It's pretty confusing, sir.
These codes,
I
right?
have shared the poll
Yes,
now.
sir.
Okay. Yeah.
It's called and the before code you used to show the three different images and that images you set to export from the white image which is that nothing and you show the separate bands and enhance the image. Last code, sir,
Okay.
I can't able to understand. So you went too fast.
Okay.
Yeah, yeah.
Just wait. Just wait, Pratik. I'm sorry for interruption here at this point. There are two things. This recording will be later available, and in this particular course, we are really not focusing while designing with Varun. We decided we are really not focusing on the image processing aspect. So fits file for data and those things are fine. Image processing is itself a course in itself. So we may probably go for next winter school with image processing, something like that. So later you can see what was done. And of course, you can ask these questions on the group. Sorry, Pratik, for this, but we had to.
Yeah, no problem. Yeah, I understand. So I have written the comments for this code in the notebook that I'll share. I'll write maybe more explanation about what I did here, so you can read it for yourself when I share this notebook.
Okay, sir. Thank you.
Yeah.
You can find the polls in the more option. The poll is already there. It has not ended. The next session will start at 2:30, our regular time. It will be posted on the group. And if you have looked at the schedule, then you know what are the different things that we are going to discuss in this particular winter school. So please see the schedule, which is already posted on the group. Okay. I will end the poll here. Shekhar, sir.
So let us take this opportunity to thank Pratik and Jigar both for taking us through this wonderful journey of how to uh, understand the constants, how to write equivalence, astropy coordinates, right? Color bar fets, how to import data. So I think it was a wonderful session, and all of us enjoyed it. And I think the assignment is there, so it will be helpful. This session will be helpful in solving the assignment using the constants and all those things. Thank you, Pratik and Jigar again.
Thank you.
I think we'll meet for the next session. Thank you, everyone.
Yeah.
Thank you all.
Shubham, we can